This should be a pretty quick video on partial fractions from section 8.5. We are only going to be dealing with what are called non-repeating linear factors for partial fractions. If you're reading through the textbook for section 8.5, you'll see a lot more material on partial fractions that we are not going to be covering, but we will be covering what's required for the AP test. To put it as simply as we can, as it says up here, partial fractions is simply the idea of breaking a large rational expression or large fraction into a sum or difference of smaller fractions. If you can do this, then it's easier to integrate an expression, because when you have a sum or difference, right, then you can just integrate each piece of the sum or difference separately. All right, so looking at the example we have here, first thing I would look for is, could I use maybe the natural log rule, since I could think of my denominator as my inside function. Therefore, I might first try to rewrite this as, the integral of x squared plus x minus 2 to the negative 1 times 3x dx. Of course, maybe what I should do is pull that 3 on out, so let me get rid of that, and I can pull that out to the front. But I can see that, this is not going to allow me to use the unchained rule, because the derivative of my inside function is 2x plus 1, and there's no way I can get that in here. I could get a 2x, but the plus 1, we're not allowed to add a constant inside an integrand. Therefore, what we're going to do is break this fraction up, and you can do this as long as the denominator is factorable. So if we take a look at this denominator, we would have what? X and x looks like a plus 2 and a minus 1. Alright, so that means that we could rewrite this fraction. Let's see, we have 3x over x squared plus x minus 2. We could rewrite it as a sum of two fractions where one of the denominators is x plus 2 and the other denominator is x minus 1. Now we're not sure what the numerators are, so we're just going to call them capital A and capital B. Now what I want to do is focus on just the numerators and try to figure out what A and B are going to be. So to get rid of the denominator, I'm simply going to multiply both sides of this equation by our big denominator, x squared plus x minus 2. Of course, that's just going to cancel out the denominator here. And when I multiply by x squared plus x minus 2 over here, of course, I'm going to have to distribute that. So what we'll end up with here is, let's see, remember this is just the factors of here, x plus 2 times x minus 1. Alright, so when I distribute those two factors over to the first fraction, the x plus 2's are going to cancel, and I'll just be left with a times x minus 1. And when we distribute those factors to the second fraction, the x minus 1's are going to cancel, and I'll be left with b times x plus 2. Alright, and this will all equal just 3x. Another way to look at this situation is you could just ask yourself, so if I was to add these two fractions together, get the common denominator, that would mean I'd have to multiply them together to get this x squared plus x minus 2. And in doing that, I would have to also multiply the top of this first fraction by x minus 1, and that would give me the a times x minus 1. And I would have to multiply the second fraction, the top of it, by x plus 2, since I'm also multiplying by x plus 2 on the bottom. That would give me the b times x plus 2. And then of course these two expressions here, when we add them together, have to equal 3x. But I think the easier way is just to, let's get rid of the denominator by multiplying both sides by the x squared plus x minus 2. Okay, so now here's how we can solve for a and b. Okay, keep in mind that x is a variable, so it can be any number. And what I'd like to do is I'm going to let x equal 1 to begin with. Now if I do that, then I will have 3 times 1 equals a times 0 plus, let's see, b times 3. which means I have 3b is equal to 3, so that lets me know that b must equal 1. And we're going to repeat that process to solve for a, and of course to do that, we need to let x equal -2 so that this second term becomes 0. Why don't you do that and see what you get for a, for a capital A. I'm going to go to a new slide and you can check your work with what I've done. So see if you got this for a. So here we go. We let x equal -2, which means we'll have 3 times -2 is equal to -3a plus 0. So it turns out that a is equal to 2. Alright, so now we can return to our original problem where we were trying to integrate, let's see, 3x over x squared plus x minus 2 dx. And we have found that we can rewrite this fraction as, let's see, we had a is 2, so that would be 2 over x plus 2 plus, and our b was 1, so 1 over x minus 1 dx. And now this becomes a pretty simple integral to do because we can split it up. I'm just going to rewrite this first one as 2 times the integral of 1 over x plus 2 dx plus the integral of 1 over x minus 1 dx. And of course, now we're primed and ready to use our natural log rule. And our inside function is just x plus 2, so we just need a 1 in front of the dx, which we already have. So it's just 2 times the natural log of the absolute value of x plus 2, whoops, and then plus the natural log of the absolute value of x minus 1, and plus c. And we are done. I need to show you one more example where the situation is just a little bit different. It turns out that this partial fractions method works as long as the degree of the numerator, okay, is less than the degree of the denominator. If that's not the case, then you should first use long division to just break the fraction up into a sum or difference. And you're going to have at least one problem on the homework you do where you have to do this. So you can see with my example here that we have the same degree on both the top and the bottom. So we don't want to mess with partial fractions just yet. First of all, I would take a look at it and see, can I use the natural log rule? Look at my denominator. We could even rewrite it here as, let's see, the integral of x squared plus 2x minus 3 to the negative 1 times x squared minus 5x plus 7. Let's make that look more like a 5 dx. But I don't think we're going to have any luck because our derivative would be 2x plus 2, and there's no way we're getting that. Okay, so scratch that out. Whoops. Scratch that option out. And now we're going to kind of split this fraction up just a little different way, but this is something you've done before, right? We're just going to take x squared plus 2x minus 3 and divide that into our top fraction, our top polynomial, x squared minus 5x plus 7. Alright, and of course with long division we check out the x squares. We say how many times does x squared go into x squared, and that would just be once. Now we multiply the 1 times the x squared plus 2x minus 3, giving us x squared plus 2x minus 3, and then we subtract. The x squares cancel, as they always will, and then we'll have negative 5x minus 2x, so negative 7x, and 7 minus negative 3 plus 10. Alright, and we can't do this again because x squared won't go into negative 7x, so this is our remainder. Okay, we have our quotient, we have our remainder, and then we have our divisor. So we can rewrite this fraction right now as, and I say this fraction, I'm talking about this one up here, can be rewritten as 1 plus, okay, it's our quotient plus our remainder, negative 7x plus 10, over our divisor, x squared plus 2x minus 3. Right, and in doing this now, we're already starting to split the fraction up so that we can take the antiderivative of 1, and now we need to be able to take the antiderivative of this fraction. So let's go to a new slide and we'll deal with that. So we now have broken up our fraction here. I've rewritten it, and we know obviously we can take the antiderivative of 1, but we still need to take the antiderivative of this fraction. And as we look at it, I don't believe we can use the natural log rule because we would need 2x plus 2 once again for the derivative of the inside function, and we don't have that up here. So what we can do now is try the partial fractions method on this, because now we have the degree of the numerator smaller than the degree of the denominator. Just to check and make sure we can do this, let's see if we can factor our denominator. I believe we can. It's x, and I believe a plus 3, right, and a minus 1 would do it. So since that checks out, why don't you take it the rest of the way? See if you can end up with two fractions where x plus 3 is one of your denominators and x minus 1 is the other. And then once you have that split up, you should be able to take the antiderivative. It might be a little more complicated than the one we did before. I think you're going to end up with maybe some fractions for the a and the b. But don't let that bother you, because you can always just pull those fractions outside the integral before taking your antiderivative. Alright, go ahead and pause the video and see what you can do with that. Check and see if your work looks like this. Okay, so if we set up our fractions here, then we can multiply both sides by the x plus 3 and the x minus 1 to cancel them out, and we're left with negative 7x plus 10. And we do that on this side, and the x plus 3 will cancel, leaving you with x minus 1 times a, and then the x minus 1 cancels in this term, and you'll have b times x plus 3. And once you have that set up, then we'll just let x equal 1, so this factor will become 0, and we get that b is 3/4, and then we're going to let x equal negative 3, and when that happens, we get a to be 11/4. So all we have left to do now is the integration. If you haven't finished that, go ahead and do so, and then you can check your work on the next slide. So we kind of took this problem in several stages. First, we realizing that our degree on top was the same as the degree on the bottom. We couldn't do partial fractions just yet, but we did long division and found that that would equal 1 plus our remainder here, the negative 7 plus 10, over our divisor of x squared plus 2x minus 3. So we're able to split up this integral, but the only way to really get to this one is to go with partial fractions. So we focused on that and found that you could rewrite this one big fraction as 11/4 over x plus 3 plus 3/4 over x minus 1. Alright, and now we can split up our integral for each of these three terms, as we've done here, and as we do that, I'm just going to pull a constant 11/4 out front, and the same thing with the 3/4. And now that we have this is not hard at all. We can use our natural log rule on each one of those, or on the second two integrals. If you would like to see another example, I encourage you to look at page 554, and you could look at example 1 where they do another one. And also, you've actually already seen this this situation before. If you go back to page 427, you will see that we used partial fractions to determine the solution to the logistic differential equation. Alright, it's under example 9. Logistic diffq. And that gave us, I believe it was y equals L over 1 plus b times e to the negative kt. I believe that was the solution we got, and it took partial fractions to get there. Okay, well, check Whipple Hill for the assignment. It's just a few problems, and you can get a little more practice with this method.